Okay, I was thinking when Eb was talking that actually until I moved to Illinois in 1969, I actually worked with rhesus monkeys. And collaborating with Kara Pribram and other people, we actually did a lot of, I think, very good work. And then for some reason having to do with politics in India or whatever, when I got to Illinois, the rhesus monkey jumped from $75 per monkey to $2,700 per monkey. And I didn't think I have the budget for that. And I didn't know what to do. And then I taught my first class. There were about 100 students there. And I looked around the class and I said, gee, they're all primates. So I changed my subjects, and since the late 60s, 69, we've been studying humans, mostly undergraduates, except for patients that came up in the BCI research. Okay, basically, we need to distinguish when we're thinking about using any kind of electrophysiological activity or neural activity. There are two methods. One is what I call eavesdropping on the mind, and the other I call diagnostic monitoring. Eavesdropping on the mind has been proposed in the various programs that I have been participant in. Is simply the belief that all you had to do is analyze the EEG or the MRI nowadays, the fMRI nowadays, and you can listen to the conversation inside the brain because the words will sort of emerge from the noise or from the signal. And I'm not particularly enamored with the results of this research. The other approach is what I call diagnostic monitoring, where you make inferences about what the person wants to do, what the mind is trying to do, what the person understands, what the person recognizes, by interpreting brain signals in some way which allows you to do that. So in direct eavesdropping, you decide that the couple actually know French because you hear them talk French to each other, and they seem to be responding correctly, which of course may only mean that they're playing a game, but at least that's the idea. In diagnostic monitoring, you decide that they know French because when they're watching a French movie, they laugh at the proper place in the narrative and are not waiting for the subtitles to appear so they know there was a joke. And I remember many years ago, my wife and I went to an Israeli movie in Beverly Hills, and we could tell which group in the audience were Israelis because they laughed at the right place, and most of the other audience waited for the subtitles and then they laughed. And so you could infer that at least the people who laugh in the right place must know Hebrew. That doesn't always work. Many years ago I was trying to illustrate, I think it was 3 years ago at the previous meeting of BCI meeting, I gave an example of how we were using the same oddball paradigm in P300 for guilty knowledge tests. And I told the audience, here is a list of character strings. Some of them are words in English, some of them not. And I want you to pull on your left ear when it's a word in English and pull on your right ear when not. And I showed them about 16 or 14 different strings. And then I showed all the strings together again, and I showed about 4 of them. I said, well, those are actually names of flowers in Hebrew. And my wife sitting in the back there, she probably knows that. Now, it doesn't mean that she's an agent of the Mossad, but at least it means that she knows Hebrew. But it turned out I was FOS, because during my presentation, Teresa turned to my wife. They were sitting next to each other, said, what is Manny doing? He's putting names of my girlfriends in the list. And it turns out that we do, in Israel, they do give names of flowers to women. and Teresa happened to know Shoshana and Rakefet, and so it doesn't always work. You really have to be careful about the inferences you make. But at least that's the idea. So let me go quickly to a lot of the work that we have done in the 70s and 80s, which eventually led to the development of the BCIs, you will see, was within the framework of a program that DARPA supported very well. It was called the Biocybernetic Program. And the mission of the Biocybernetic Program was to make inferences about the operator using psychophysiological signals that would improve the communication between the operator and the system. And it was driven by the perception, which is very correct, there's a tremendous imbalance between the amount of information the machine can give the operator and the amount of information the operator can give back to the machine. And DARPA was under the belief that we could improve the situation by getting information physiologically from the operator and enhancing the person-machine. Actually, in those days, they called it man-machine interaction, but I've been an administrator long enough to know that you should say person-machine relationship. But so they actually supported this very well. I don't want to go into great detail, but the funding level was wonderful. I can tell you a simple anecdote. Sometime in the 80s, I was a member of an NIMH study section, and we got a grant proposal from Eric Kandel, couldn't be more distinguished, asking for $5,000 because he moved from wherever he was to Columbia, and he didn't get all the equipment he needed, and he needed $5,000 to complete his equipment. I was primary on that one, and I said, of course, give him the $5,000. But the rest of the committee got very upset, and they said, why, if Columbia wants Kandel, they should come up with the $5,000. You give it to Kandel, some junior investigator will not get it. And the discussion went on for about an hour. At that point, I had scheduled ahead of time to call my contract monitor at DARPA. So I go to the public phone next door. You remember those, and I dialed the number, and he says, George, this is Manny. He says, oh, Manny, what do you want today? And I said, well, you know, this Harris machine we're buying, we really need another disk, and it's $15,000. And he said, you got it. I hung up the phone, and that was the end of it. And I went back into the study section. They were still arguing about Kandel's $5,000. So actually working for DARPA was actually quite a pleasure in those days. Now, one of the contractors in the BCI, in the Biocybernetics program, was Jacques Vidal, who was a professor of computer science at UCLA. And he developed what is clearly an early version of brain-computer interface. Now, in Vidal's task, the operator, the subject, has to move the mouse out of the maze. The mouse is this little red triangle. And he does it, or she does it, by focusing on one of the four circles above, below, and to the two sides of the maze. The circles contain a checkerboard that's fluctuating, each checkerboard at a different frequency, different by 1 cycle per second. And there was enough data by then showing that if we focus on a checkerboard that's flickering, you'll get a lot of alpha activity from the occipital electrodes. You'll get EEG driven by the frequency of the checkerboard. So Vidal developed this idea that you could actually, and he actually successfully moved the mouse out of the maze using this technique. He was one of the contractors in the Biocybernetics program. You could argue, of course, that you could do exactly the same thing by recording eye movements. But the point he made was valid, and that was an example of the Biocybernetic program. We, by that time, became very involved with the issue of measuring workload, which is a big deal in this engineering psychology, human factors area. And workload is different than task difficulty. Workload is an interaction between task difficulty and operator capacities, and it's not easy to measure. And this is an interesting study by Frustofer that showed some rather surprising results. In those days, you know the trains in Europe that go on for hours on end, and they were afraid the operator falls asleep in the middle of the operation. So they put in the dashboard a light that flashed every so often, and the driver had to push a button right after the light flashed, and then they'll know that he is still awake. The problem was that Frustofer did this study and recorded EEG continually during the night, and there are episodes in which the driver is showing the EEG of deep sleep, but he's still pushing the button exactly the right way. So it wasn't all that reliable a measure of workload, and so they got interested in doing it some other ways. We decided to use the oddball paradigm, which is a basic element, and I'm going to talk a lot about the oddball paradigm, I think, Wednesday evening. And I'm going to talk to this group about it a lot because I end up reviewing a lot of papers that journals send me to review, and 90% of these papers display a complete failure to understand how the oddball paradigm works and how it could be used in a BCI. So I thought a tutorial on that topic might be useful for this meeting. But in any event, the point about the oddball paradigm is you have a sequence of events, and the events can be anything. Can be light flashes, can be abstract events or whatever. And there's a task that the subject has to perform which requires them to respond to each event, but classify the events into one of two categories. One category appears rarely, and the other category appears frequently. And the rare events elicit a P300. That's the oddball paradigm. It's not the target. It's not the target that elicits the P300. Let me repeat that. Perhaps it will sink. It is not the target, it's the probability. That's absolutely critical to understand. So here's the proof. This is a study Connie Duncan Johnson and I published in 1977. And in this is just a bunch of oddball paradigms run concurrently. In each case, in all cases, the high tones were the targets. But they change as you go up the column, they change probability. And you can see that depending on the probability, the high tone does or does not elicit a P300. And whether it's a target or not is completely irrelevant. There's a little target effect, but it's basically irrelevant. So that was the kind of knowledge we had when we started dealing with the BCI. Now, well, I'll skip that. We use that for the workload measurement. Now, at some point in the middle 80s, a young man, about 20 years old, fell off a silo in the Champaign-Urbana area and basically became paralyzed. He broke his neck, became paralyzed, was unable to speak, and was quite paralyzed. His mother was sure that he's locked in, that behind that paralysis there's a mind that can talk, and the physician that was treating him wrote Craig Fields, who was then the director in DARPA of the program, and said, well, I've got this kid who looks like he's locked in, and I've heard that you people have developed methods for measuring bodily functions and making inferences about consciousness and the ability to communicate. And Craig Fields answered him, well, it's sort of funny that you write me from Champaign-Urbana. What I suggest you do is you find a psychology building, find Emmanuel Donchin in the psychology building, and tell him your problem. We shoved enough money down his pocket. He should be able to solve it. That's literally a quote from the letter. He should be able to help you. And he showed up, and Larry Farwell and I took on the task and developed what we eventually published in 1988, Talking Off the Top of Your Head. And the basic idea was we presented the subject with a matrix of 6 by 6 cells, which contained the alphabet plus a few additional signals. And we did not want to, and we didn't think it would work, to ask the subject to focus on the letter he wants to type and then check every one of the 36 letters to see if it elicits a P300. What we said is we're presenting you with 12 stimuli, 6 rows and 6 columns. And you're supposed to pay attention to the cell in which the target exists, but what you're getting is an oddball paradigm with 12 events. One category has 2 events, which is the row and the column that contain the character that you're thinking of, and the other are not. And we predicted, given what we knew about the P300, that only the row and the column that he was focusing on will elicit the P300 and the other will not. And to our, I suppose, not really great surprise, but it certainly reinforced our self-approval. We got exactly what we predicted. Those are not patients. Those are just 4 primates that we borrowed from the class, and they were run. The flashes were run at 125 milliseconds per flash, or 250. It really didn't make a big difference. It was a little bigger, but you can see that in each of the 4 subjects, the row and the column that contained the character were in fact eliciting a P300, and the others did not. And that was basically the idea of this P300 BCI, that you use the oddball paradigm. You have 12 items, and the fact that there are 36 different items is not relevant, because the subject is focusing on the character that he wants to communicate, and the row and the column containing this character are what is important. We used a variety of ways of detecting the P300. I won't bother you with the details, but there are various ways of detecting on a trial-by-trial basis where there's a P300. And it turns out almost everything worked fine. Stepwise discriminant analysis worked best, but it wasn't the only one. This shows the data for just 2 subjects, and you can see that it rises to a maximum very rapidly. So this is all from the very first paper. Now here's some real data. What you see here is the individual traces for each of the 36, each of the individual rows and columns. And the red line is the targets. The dark blue line has 1 target, 1 non-target together, and all the others are mixed. And the person on the left is a control subject, perfectly normal, and as normal goes, but certainly not damaged in any way. The next person is an ALS patient who was actually quite able. And then below that are 2 other ALS patients, and actually even in this ALS locked patient, was really in bad shape, we could still detect the red line more easily. So this worked quite well. These are data showing the progression over 10 sessions. With these are actual patients. Eric Sellers ran this data, and it was quite clear that it works well. Well, we kept doing that, and we got a lot of data. One thing which turned out to be very important, at some point, it was actually after the very first BCI meeting, the one that was at Rensselaer. It was attended by Ingrid Wickelgren, who is the daughter of Wayne Wickelgren, who was an ALS locked-in patient, and she is the writer for Science, and she attended the meeting. And at the very end of the meeting, we had a session. You may remember that. She said, "So what are you going to do for my father?" And in the end, we actually went, we took all our equipment, with nowadays it's just a BCI 2000, which is sort of portable, but in those days it was big grass amplifiers and a big computer and display and so forth. And we went to New York. And one of the things we discovered when you go into real life, the Wickelgrens at the time lived in one of these Columbia faculty housing on the west side, which are very long train-like apartments. And they had a dog. And the dog had control of the house. And the dog thought that our cables and wires are really exciting. And it presented us with a challenge that never came up in the lab. And it was an education. Eventually we figured out what to do, but life in the lab is not as complicated as life on the west side of Manhattan. So in any event, this just shows that we can get, I think that's about, well, this is, one other thing. At some point, I gave a talk in our engineering college, and one of my colleagues there developed a robotic arm. And he said, I control the robotic arm by moving a joystick, but not all my subject can do that. And I said, well, of course, we can use the P300 to control. And the next thing we knew, we developed a version of the oddball paradigm alphabetic by showing arrows and movements and so forth. And we allowed subjects to control the robotic arm, watching the flashing lights. And I'm afraid I can't show you, because for some reason it doesn't quite work here, the movie that we made of that, because this is bits Hitchcock at his best. The idea is that the robotic arm is supposed to pick up a cup of coffee and bring it to the subject. And at the very end, you've got about 5 seconds where it's not clear if the robotic arm is going to turn the coffee over or give it to the person. And there's a lot of tension in that movie, but I'm going to spare you and not things. So basically, the conclusions are ERP components can be used to support diagnostic monitoring. The issue is appropriate choice or development of the task. Signal analysis is crucial, and assessment is a must. Thank you for your attention.